Welcome to Math TV with Professor V. In this video, we're going to learn about the comparison theorem for improper integrals. So first we're going to go over the statement of the comparison theorem and then work through several examples so that you can become a professional at mastering this concept. So here's the basic statement. Suppose that f and g are continuous functions with f of x greater than or equal to g of x greater than or equal to 0 for all x greater than or equal to a. Part A. If the integral from a to infinity of f of x dx is convergent, then the integral from a to infinity of g of x dx is also convergent. B. If the integral from a to infinity of g of x dx is divergent, then the integral from a to infinity of f of x dx is divergent also. Don't memorize which one's f, which one's g. That's irrelevant, okay? It's not going to be useful when you're trying to apply the theorem. What's useful is understanding the essence behind it and what the inequality is that's necessary to draw a conclusion. So here's what's going on. Here's a little graph. Hopefully it'll be helpful. Let's break it down. Break it down, people. So we're assuming just in this statement here that f of x is greater than or equal to g of x. And we do require that they not be negative in order for this theorem to hold. So look at what this is saying. If the integral from a to infinity of f of x dx, the larger function, is convergent, then the indefinite integral from a to infinity of the smaller function g of x dx is convergent also. So think about it this way. When you first studied integrals, you learned that the definite integral from a to b, right, when this is a finite number, of f of x dx represents the area underneath the curve of f of x from a to b. Obviously, when we change the limit to infinity, then it becomes a little funky to think about, like, how do I accumulate area on an interval that has no end? But the idea is we say an improper integral is convergent because the sum of all this area doesn't blow up. It doesn't go to infinity. It approaches a finite number. That limit exists as a finite number. That's what it means when we have this convergent improper integral. And it's basically because, as you keep adding more area way out here, it's so small, the amount that you're adding, it's almost insignificant. So the sum approaches some finite number. And so if you have this other function g of x and it's smaller than f of x on this entire interval, then of course the area under this curve should sum up and approach a finite number as well, right? If I know the area under f approaches, the sum of all of that approaches a finite number, that integral is convergent, then this one should be too. Now we have another way to look at this. Again, we're assuming g of x is the smaller function. So part B statement says, the sum of the area under the curve of g of x from a to infinity, so the limit of all of that area, diverges, meaning it blows up, it approaches infinity or something, doesn't exist. Then this function, this larger function, will diverge as well, that improper integral from a to infinity of f of x dx. That should make sense because if the sum of this area under the curve from a to infinity, that limit does not approach a finite number, it blows up, and this function's accumulating more area, then it will blow up as well. So the direction of the inequality is important in order for you to draw a conclusion because there's really 4 cases. Only 2 allow us to make a conclusion. What are the other 3 cases that are not listed? Well, if the integral from a to infinity of f of x dx, what did we not say? If it is divergent, then we have no info on the integral from a to infinity of g of x dx. So think about it this way, and I'm just assuming f of x is the larger function. This indefinite integral diverges. G, that indefinite integral from a to infinity of g, it could converge or it could diverge also. It has some options. So this situation gives me no info. What's the other situation that gives us no info? I will list it down here. So if the integral from a to infinity of g of x dx is convergent, where g is the smaller function, then again, I have no info on the integral from a to infinity of f of x dx. So if the smaller function, the indefinite integral from a to infinity of the smaller function converges, well, the integral from a to infinity of the larger function, it could converge as well, or it could diverge. I'm not forced into a certain conclusion, all right? So don't memorize which one's f, which one's g. Just understand, if the indefinite integral of the larger function converges, that forces the smaller to converge also, because we require them to be non-negative. So this is kind of like your boundary. So if this one smashes it down and approaches a finite number, then the baby one gets smashed too. And then similarly, in terms of blowing up, if the indefinite integral of this function from a to infinity blows up the smaller one, then the bigger one must blow up also and diverge, okay? Blowing up means diverging to me. I think of it that the limit of the area that sum is not a finite number, okay? So it is tricky to work with the inequalities. Also, you have to show a certain direction of inequality, right, to have a conclusion, which means you already have to have an idea that your integral is going to converge or diverge from the get-go. Because do you want to show that it's smaller than another function, or do you want to show that your function's bigger than another function? For you to get anywhere, you already have to have an inkling. So this is a very difficult theorem to master, okay? Be patient with yourself. And just, it takes practice. Talk about it out loud to your friends, your neighbors, the more you talk about it, you'll sound these ideas firmly in your brain and in your hearts. Okay, so one key basis, which you should have seen already, that helps us apply the comparison theorem has to do with p-series. So if you have an integral from 1 to infinity of 1 over x to the p dx, this should have been proven to you in your notes, in your lecture at some point in this lesson. We say that this integral is convergent if p is greater than 1, and it's divergent if p is less than or equal to 1. And then I do want to make a note that the comparison theorem can also be used for improper integrals, not of the type where one limits infinity, but where one of the limits is a discontinuity in the function. We can apply it in that case as well. So I will show some examples, okay? Are you ready? Get a snack, get a drink, get comfy. Here we go. Decide or determine whether the improper integral converges or diverges. They're not telling me to use comparison theorem, but we're going to use it the whole video. If they didn't tell you, how would you know? Kind of mean if they don't tell you, honestly. I would say, because if you look at this function, it's not something we can easily integrate, okay? I know you learned so many techniques, but try, it won't work nicely. Okay. So let's start thinking to ourselves, do we suspect that this integral will converge or diverge? What's your guess? Look back at p-series. Look back at p-series. They will help you. 1 over x to the p dx, that improper integral from 1 to infinity converges if p is greater than 1. Okay? The exponent on x if it's greater than 1. Look down here. The exponent on x is a 2. I know there's a sine squared x in the numerator. I know. But because this is basically growing like the p-series, 1 over x squared, I'm suspecting, okay, let me write this down for you. We suspect this integral converges. So, in order for me to use the comparison theorem and show that this integral converges, I need to show that it is less than some other integral that I know is convergent. So I need to show an inequality that establishes the fact that this function right here is smaller than another function. I think we can do it pretty easily. No? Yes. Sine squared x over x squared. I know sine of x is always bounded between 1 and -1. So sine squared x is for sure going to be less than or equal to 1 over x squared. And this is true on the entire interval in question, the interval from 1 to infinity. I mean, it's always true, but hey. And so in terms of the statement of the comparison theorem, if we want to go back, f of x is the larger function whose integral from a to infinity is convergent. Here we've established it. Basically, like, this is your f of x, and we have g of x. But I told you, like, don't get hung up on which one's f, which one's g. It's irrelevant. It's irrelevant. We know that the integral, and the limits must match. So we're going from 1 to infinity. So 1 to infinity of this function here, that's 1 over x squared dx. What do I know about this integral? I know this is convergent. Justify why. Don't just go putting blatant statements on your paper, because it's a p-series. P equals 2, which is greater than 1. So therefore, I already showed the desired inequality. My function sine squared x over x squared is smaller than 1 over x squared, so the improper integral from 1 to infinity of that function also converges by comparison. And that's it. How nice. P-series are very helpful when using comparison theorem, because you don't have to actually sit there and evaluate an improper integral. Okay, it's already proven. How lovely. Let's try another. Are you ready? Just keep practicing. If you need a pep talk, just tell yourself, no one came out of the womb using the comparison theorem to evaluate improper integrals. It's just with hard work and practice that you can become a professional and do these effortlessly. Okay, integral 1 to infinity, 1 over rad x squared minus 0.1 dx. Okay, we have to figure out, what do we suspect it's doing? Yeah. In order to do that, I say just look at the leading term in the numerator and denominator of the function that you're trying to integrate. So here's our function. There's just a constant in the top, okay? And then in the denominator, just look at the leading term. 0.1's not doing much. I have square root of x squared. Okay, square root of x squared, that's technically, do you remember, absolute value of x. Notice here we're integrating from 1 to infinity. So on 1 to infinity, x is always positive, so I can just simplify this to 1 over x on 1 to infinity. Now, what do we know about 1 over x? Well, the integral from 1 to infinity of 1 over x dx, that diverges. Why? Because it's a p-series, p equal to 1. The exponent here is a 1, right? We don't write it. P-series only converge if that exponent p is greater than 1. Okay, so let's think here. I suspect this improper integral diverges. I have another one that I know diverges. In order to use the comparison theorem, I need to show that this function here is greater than or equal to 1 over x. Can I do it? Can I do it? Let's see. Usually they're written in such a way that you can. Yep. So 1 over rad x squared minus 0.1. Let's think about it. I want to show this is bigger than something. Ooh, how can I do that? Well, if I get rid of minus 0.01, okay, notice here, subtracting a number makes this denominator smaller. And when the denominator of a rational expression is smaller, the overall expression is bigger, right? So this is greater than or equal to 1 over if I had just rad x squared. Take a second and think about that. I just made the denominator bigger here. So overall, this expression is smaller. And then the rest of the inequality just falls into place. This is greater than or equal to 1 over absolute value of x, which is 1 over x on 1 to infinity. So we're done. So therefore, I showed what I needed. This means the integral from 1 to infinity of 1 over rad x squared minus 0.1 dx diverges by comparison. All right, how are we doing? It's uncomfortable, I know. We're just gonna have to keep practicing. So onward and upward. Here's a different type of improper integral. Okay, notice this one's improper because at the lower limit 0, rad x is equal to 0, so this function here is undefined. What do you suspect is happening? Oh, I don't know. It's difficult. You cannot use p-series. Don't think about p-series. Cannot use p-series. Why? Well, p-series only work as long as the lower limit goes from 1 to infinity, 1 over x to the p dx. You could change it so this limit goes 2 to infinity, 3 to infinity, whatever. It cannot go 0 to infinity because then the denominator would be undefined. So only use p-series if you have a constant. Usually it's 1 to infinity. This is not that. This is not that. Okay? I don't really have a strong inkling one way or another. I just know, generally speaking, because cosine's bounded, cosine of x is bounded, it doesn't really affect a function the way it grows or shrinks all that much, the way variables, other variable terms do. So I'm inclined to say it might converge. Let's see. So cosine x over rad x, I know that's less than or equal to 1 over rad x, right? Especially on the interval from 0 to pi over 2. And this is much easier for me to integrate. So already, can you tell what I'm suspecting? I just showed that the function whose integral I'm trying to evaluate is smaller than another function. So we suspect our integral converges. Okay, so let's try. Let's see. Okay, so 0 to pi over 2, 1 over rad x dx. I have to immediately change that lower limit, replace it with some dummy variable of choice. How about a to pi over 2, and then we have the limit as a approaches 0 from the right. And again, if you get confused, is it from the left or from the right? Just go like this. The original interval went from 0 to pi over 2, yes? The only way to approach that lower limit of 0 is from the right side, okay? And then 1 over rad x, I'm getting ready to integrate. I'm going to write that as x to the negative 1/2. Are you with me? Oh, good. Okay. So we have, keep writing, limit a goes to 0 from the right. What's next? You add 1 to the exponent, divide by the new exponent. So I'm going to have, x to the positive 1/2. Divide by positive 1/2, I'm going to have a 2, and this gets evaluated from a to pi over 2. All right, so this is the limit. A approaches 0 from the right. 2 times x to the 1/2 is square root pi over 2 minus square root of a. Now, can I take this limit as a goes to 0 from the right? Rad pi over 2 is a constant, minus square root of 0. That's just going to go to 0. And we're approaching from the right, so that's going to be well-defined, non-negative numbers. And then I'm just left with 2 times the square root of pi over 2. And you can write that as 2 rad pi over rad 2. This rad 2 cancels, and now I just have rad 2 in the numerator. Rad 2 times rad pi, I could put them underneath the same radical, rad 2 pi. So as long as you get a finite number, that means your improper integral converges. And we just showed that the function whose improper integral we were trying to evaluate was smaller. Yes, see, it's smaller than this function whose improper integral converged. Therefore, our integral from 0 to pi over 2 of cosine x over rad x dx also converges by comparison. Okay. Now, this one we kind of did a little more blindly than the others. Say this had not come out to a finite number, this limit, and I got infinity or negative infinity or something. You shouldn't get negative infinity because you should be using non-negative functions. But anyways, if it diverged, then I would have no information because then this integral could converge or it could diverge also. So what does that mean for you? It means either you picked a bad function to compare it to, like you picked the wrong one, pick something else, or you just need to maybe manipulate your approach a little bit, or your guess is wrong. Maybe you need to show an entirely different inequality. Who knows? Okay. So just keep in mind, if something converges, you have to show that your function is smaller than the other function. If another integral diverges, you have to show your function is bigger than that function. Okay, there's only one direction that's useful. Okay, here's another. We have integral from 1 to infinity, x plus 1 over square root of x to the fourth minus x dx. Now, in this case, can we use p-series for comparison? Why, yes, because the limits are from 1 to infinity. Perfect. Okay, this is a great example because it really helps you sound in if you have a good feel for how fast a function's growing. So here's my function. Look at just the leading term in the numerator. The highest power of x is just x to the first, so we've got x up top. And then in the denominator, leading term is rad x to the fourth. And that just simplifies to x squared. And x over x squared simplifies to 1 over x. Well, what do we know about the integral from 1 to infinity of 1 over x dx? It diverges. Yes, very good. It's a p-series. P equals 1. So hold on now, let's think. Here's an integral that I know is divergent. I need to show that my function is larger than this function in order to say that our integral is divergent also. Okay, can I show that this is larger than 1 over x? Let's try. So we have x plus 1 over square root x to the fourth minus x. Well, if I get rid of the plus 1 in the numerator, don't you agree this is greater than or equal to x over square root of x to the fourth minus x? Yes, that's true, right? Similarly, I got to play with the denominator. If I get rid of minus x, okay, that's going to make the denominator over here larger, which makes the entire expression smaller. This denominator is larger than this denominator. Therefore, this entire expression is smaller than this. Yes? Oh, good. And then we have this simplifies to x over x squared, which is 1 over x. Are you worried about something? If this had been a minus and this had been a plus, we wouldn't have been able to do this beautiful string of inequalities. And then what would we do? I know. These problems are written in such a way to enable you to set up, the necessary inequality. So don't you fret. Someone sat there making sure this was a plus, so you could do this little step here, and this was a minus, so you could do this little step here, okay? Well, we showed what we needed to show, didn't we? Here's our function. It's greater than or equal to 1 over x. This improper integral diverges. Ergo, the improper integral from 1 to infinity of x plus 1 over rad x to the fourth minus x dx also diverges by comparison. And it is worth mentioning, if you cannot show the necessary inequality, there is another kind of comparison test that you can use called the limit comparison test for improper integrals. It's usually used for infinite series, but it also can be used for improper integrals. It's not commonly taught or covered in most textbooks, so I'm not going to get into it, but you do have kind of like another nice backup plan. If you're interested in a little bonus video, let me know. Okay, I have a couple more. Number 5. Integral from 0 to infinity of x over x cubed plus 1 dx. I went on a rant earlier, right? About how p-series has to be from 1 to infinity, not 0 to infinity. But I really want to use P series. So what can you do? You can do this little slick maneuver here. You can rewrite this integral 0 to 1 of x over x cubed plus 1 dx plus, then we have this integral from 1 to infinity, yeah, x over x cubed plus 1 dx, and tackle them one at a time. One at a time. Okay. Let's look at the more fun one here. Ooh. Integral from 1 to infinity x over x cubed plus 1 dx. What's your guess? What's your gut telling you this thing's going to do? How fast is it growing in the numerator? As fast as x to the first. How fast is it growing in the denominator? As fast as x cubed. So it's basically growing like x over x cubed, which simplifies to 1 over x squared. Well, what do we know about the integral from 1 to infinity of 1 over x squared dx? It's a P series. What's P? 2, which is greater than 1. So this guy converges. So if 1 over x squared converges, in order for me to show that this improper integral converges, I need to show that this function is smaller than 1 over x squared. Can I do it? Why, yes, you can. X over x cubed plus 1, that's less than or equal to x over x cubed, right? Which is just 1 over x squared. Okay, so that's handled. So that means the integral from 1 to infinity of x over x cubed plus 1 dx converges also. As a note to the especially paranoid student, if this was a minus, we couldn't write that step. But don't worry, whoever wrote these problems is looking out for you. Okay, so that one's done. This guy converges, so this converges, cool. What about this other integral here? Now we focus on 0 to 1 x over x cubed plus 1 dx. Is this an improper integral? Improper integrals occur if one of the limits is infinity or negative infinity, or if the function is not defined anywhere on the interval. Okay, so meaning you check the domain of the function. If there's any domain restrictions and they are part of this interval, then you have an improper integral. But x cubed plus 1, that's only undefined when x is negative 1. And that's not a part of the interval from 0 to 1. So this integral represents the area underneath the curve of this function, x over x cubed plus 1 from 0 to 1. I don't need to actually find its value. I just know it exists as a finite number. It's convergent. This is not an improper integral. Nobody cares what it actually is equal to. We were just asked to figure out if the integral converges or diverges. And I can already answer that. I can say this converges, okay, because the function, I'll just call it f of x, which is x over x cubed plus 1, is defined on the entire interval, right, from 0 to 1. And so this integral represents some finite area. Okay, that's it. Therefore, overall, we have the sum of, this is convergent, that is convergent. So I know that my original integral from 0 to infinity of x over x cubed plus 1 dx is convergent. Or converges, whatever. Okay? Good. If something's not an improper integral, it will be convergent. You took that for granted prior. Okay, last one. I hope you love it so much. 0 to infinity, again with the 0 to infinity, arctan of x over 2 plus e to the x dx. Okay, so we can't use P series because we don't have x raised to some power. Who's running the show? Arctan of x isn't doing anything exciting. Do you remember what arctan of x's graph looks like? It's necessary. If you don't remember, I always tell my students, go quickly to the tattoo parlor this weekend get a few key graphs and maybe a unit circle tattooed on you. And they go, isn't that cheating? I'm like, if you're really going to commit to getting a tattoo, I think I'd allow it. Okay. Arctan of x, horizontal asymptotes at pi over 2, negative pi over 2. Why is this important? Because right away I know arctan of x is not running the show. It's not really controlling much. It's bounded between pi over 2 and negative pi over 2. Okay. E to the x, that's what's running the show. And keep in mind, exponential functions grow faster than any polynomial function. So if you're looking at a p series, but then I have an exponential function in the denominator, that's growing faster than p to any constant, okay? So I'm suspecting already that this will converge. I suspect it converges. So I need to show that this function here is smaller than something else whose improper integral converges from 0 to infinity. So let's see if we can set up an inequality. So arctan of x over 2 plus e to the x. Well, I already know arctan is bounded by pi over 2 and negative pi over 2. So for sure, arctan of x is less than or equal to pi over 2 over 2 plus e to the x, right? Good. I don't like this function yet. That's not the one I want to integrate. And I can't stop at p series, so I'm going to have to come up with something that I'm actually going to integrate. This is not it. I'm not loving it. I don't want pi over 2. It's just ugly. Pi over 2, you know, is about 1.5 blah, blah, blah. So I could say this is less than or equal to 2 over 2 plus e to the x. I still don't want to integrate that. Do you? No. So I could say this is less than or equal to 2 over e to the x, right? If I have an additional term in the denominator, this denominator is bigger. This whole expression is smaller than this one. Do we feel comfortable integrating this function from 0 to infinity? I hope. I do. Yeah. 0 to infinity, 2 over e to the x dx. Right away, change that lower limit. No, not the lower one, the upper one. Excuse me. T goes to infinity. 0 is fine. E to the t. E to the 0 is 1. We're good. And then I'm going to integrate this. So I'm going to write this as 2e to the negative x dx. Good? All right. Then this is going to be the limit. T approaches infinity. Negative 2e to the negative x from 0 to t. I'm going to factor out the negative 2. I'm not going to use it when I evaluate the limit. So this is e to the negative t minus e to the 0. Okay, I always encourage my class, when you're trying to take a limit and you've got a negative exponent, rewrite it as a positive exponent in the denominator. It just helps your brain visualize what's going on better, and you can evaluate the limit more easily. So rewrite this as 1 over e to the t minus 1, okay? So here we go. As t goes to infinity, this is a constant, not stressing. T goes to infinity. You remember the graph of e to the t, e to the x? So as t goes to infinity, e to the t goes to infinity. This denominator right here is going to infinity. A constant over something going to infinity approaches 0. So all I'm left with is negative 2 times negative 1, 2. I don't care what number it is. It could be 5,000,048. All I care is that it's finite. That tells me this integral converges. This improper integral right here converges. And I just showed that our function, where's our sweet little function? Right here. I already showed that this function is less than or equal to 2 over e to the x. And so if this improper integral converges, then our original improper integral converges also. Let's summarize it for the people. So this implies that the improper integral from 0 to infinity of arctan of x over 2 plus e to the x dx also converges by comparison. I always write by comparison because it's a theorem. You want to cite your sources. Don't be a little plagiarizer. Also, when you get into the next unit, studying infinite sequences and series, you have to cite which test you use. So this is just good training. Comparison test is used again later. So that concludes the video. I hope it was helpful. It is a difficult concept, so just be patient with yourself. Students don't like it. I'll tell you why right now, because there is not like one set methodical way to do these. You have to play around with them. You have to have a little bit of intuition. There's trial and error. Writing the inequality statements can be difficult. You kind of have a little bit more free reign than, integration by parts. There's one straightforward way to do it. You got it. You're under control, but this is more nuanced. So just practice. Be patient with yourself, but you can do it. You can do it. If you want any kind of part 2, or if you want to, it's not necessary, but it's fun to look at the limit comparison theorem for improper integrals. We can talk about that, or maybe I'll put it on Patreon or make it members only or something. So comment down below. Let me know if you found this video helpful. If you need more examples, we can make a part 2. I don't know how in depth your teachers are hounding this topic on you, but I'm here to help. You can follow me on Instagram and TikTok at Math TV with Professor V. I have got to go to ballet, so I'll talk to you all soon. Love you all. Bye-bye.